The last video, this is the data set that we generated utilizing video physics. So now what we want to do is we want to go and see if we can find ourselves. That's not what we're looking for. Nope. Oh, there it is. There it is. Let's just get ourselves a sheet here. And on the sheet, let's write out our theory. So if you remember, we have an angle here, and this is really delta theta. And we start off with an angle here, theta initial, and then we have theta final. And this is going to occur in some time period where you have initial time and some final time. And so we described angular velocity this way. We said, well, S is going to be an arc length, okay? And so if S is an arc length, R theta, and this needs to be delta theta, it's going to describe that arc length. So that means that if we know the radius, and if we know the angle, the translation, I shouldn't say translation, but the angular displacement, then we can calculate our arc length. So we did that when talking about theory, we did that in class, but any two ways, here's the theory. So now if we say, well, delta S over delta T, and we just say, okay, since we have the change in S over change in T, we know that this is going to be the translational velocity. But we can also represent R delta theta over delta T. Now, I may have been just well, no, that's fine, that's fine. And so this delta theta over delta T is just omega. And omega is our angular velocity. So delta theta over delta T is actually angular velocity, and the way we represent angular velocity is with the Greek symbol omega. Hopefully that's clear. So we have our translational velocity equals to R times our angular velocity. We're going to use this to this equation to calculate our angular velocity. So if we know that this is the case, we can write angular velocity is just equal to the translational velocity over the radius of that thing that's pivoting around a point, or that's rotating around a pivot point. Okay, so this is where we're going. Primarily when you have math like this, or when we have theoretical descriptions, it's a plan, so that we can know the next step that we need to take. It's not superfluous. It's really a plan to move forward. So if we have a data set here that we've produced, which we did with video physics, you'll notice that we have an X and a Y. So the X and the Y is going to produce our R. If you remember from Pythagorean's theorem, we can just do X squared plus Y squared, the square root of both of those products added together. Okay? And then if we want to find the velocity, we'll just use the X velocity and the Y velocity, and we can find our resultant velocity, which is what we need in this particular case. So let's do all of this wonderful mathematics. So I'm going to insert here, and we're going to call this the radius. And the radius is going to be measured in meters, so go ahead and be formal and specify that. And then we'll just wait right now to do the velocity in a second. Let's go ahead and put in Pythagorean's theorem. Pythagorean's theorem is just the square root, SQRT. And then we choose our first number, and we want to square that. So just use, let's go to 1, 2, 3 here, left-hand side. Let's use our caret squared plus the next number, which is our y position. And we're just going to square that as well. Close our parenthetical statement, and voila. We already know that it's about 10 centimeters, so this is just confirming something that we already know. So I'm just going to fill and drag down and grab all of those points. And you don't have to color code this, but, well, I'm not going to color code it. And now let's do our velocity. And let's just call it the resultant velocity. And we know that velocity is measured in meters per second. So just make sure you're very formal there. No ambiguity whatsoever. And we're going to use Pythagorean's theorem again. Yes, it can be applied to position or displacements, velocities, accelerations, forces, anything that's like a vector, you can apply it there. So it's possible even scalars. I don't see why scalars would be excluded. So let's see here. We have resultant velocity here. This is going to be equal to the square root SQRT. Again, let's choose our first number. Probably could have just copied the last formula, but oh well. Squared plus this formula. All right, so the resultant velocity is 1.62, and I'm just going to drag this down. Okay, and we want to get the average of that. So let's take the average of this. And remember that the average helps to remove the error. Oh, do we want to do that yet? No. I'm making a mistake. Short break, guys. So I'm making a mistake here. We now need to calculate the angular velocity. And the angular velocity, again, is going to be velocity, this velocity here, this velocity right here, over this, this radius. So let's do that. So this is equal to the resultant velocity divided by the radius. So we see our average, and I should have really, it's not really average, it's actually angular velocity that we're calculating. So and know that your angular velocity is going to be measured in radians per second. So now that we have that, I'm just going to go ahead and copy, I'm going to fill and drag down. And all of these numbers should remain the same based on our previous experiments. And it just looks like it's slowing down like in the beginning and the end here, or in speeding up. It's speeding up at the beginning and the end. But any two ways, we'll just take our average velocity, average angular velocity. And so again, this is going to be in radians per second. And we know how to do that fairly easily thanks to Jessica. So this is going to be equal to the average of column H. Oh, I didn't do that right. So I'll just say equals to, and let me do this, AVER, VER, average of column H, and return. And you'll notice that we have something around 13.74, which is fairly consistent all the way through. Kind of nice. We can remove like most of those decimal places. We can just go down to 3 and just pretty much stay right there, okay? And we're going to do the same thing for the 1.8 millivolt, okay? So do the same thing for 1.8. This is 1.81. Uh-oh, I think I did the wrong one. But any two ways, do it for 0.61 now. So we're going to do the same thing for 0.61 and for 1 millivolt. All right.